Hey, this is Kyle, and I'm going to be talking about dimensional analysis. We have a situation that we want to describe. It is a vertical pipe with liquid flowing down the sides of the pipe and a vapor flowing up in the pipe. So we want to find a relationship with some dimensionless numbers that can help describe our situation. So the first step we want to do is think about what variables could have an impact on the situation. So I'll write those out. So some of the variables could be a mass transfer coefficient. It could also the diameter of the pipe could have an impact. The mass diffusivity will have an impact. The velocity of the fluid will have an impact. The viscosity of the fluid will have an impact, and the density of the fluid is going to have an impact. So now we know the variables that are going to have an impact on the situation. We want to take these variables to base units. And I'll use meters, seconds, and kilograms. So the mass transfer coefficient is meters per second. The pipe diameter is just meters. The mass diffusivity is meters squared per second. The velocity is also meters per second. The viscosity is kilograms per meter second, and the density is kilograms per cubic meter. This is going to help when we make our dimensional matrix. So for the dimensional matrix, we want the rows to be all the base units, meters, seconds, and kilograms, and we want the columns to be all the variables that describe our situation. So I'll write that out. So first, for the rows, we'll do kilograms, meters, and seconds. And then for the columns, I'll do the mass transfer coefficient, the pipe diameter, the mass diffusivity, the velocity of the fluid, the viscosity of the fluid, and the fluid density. And what we want to do here is basically say, where this unit is at in the variable. So, for example, in the mass transfer coefficient, since it's meters per second, what you want to put in the matrix is the power the base unit is to. So meters are in the numerator to the first power, so this would be a 1, while seconds are in the denominator, so that is basically to the -1 power. And then kilograms are not a part of that, so that's going to be a 0. And we're going to do that for all the different variables. So I'll run through and do that real quick. So pipe diameter is just meters, so that means this is 0 and that is 0. Mass diffusivity is meters squared per second, so this is a 2, and second is a -1. Velocity is meters per second, so we have no kilograms, meters to the first power, and second to the -1st power. Viscosity is kilograms per meter second, so kilograms per meter, and then meters and seconds are both -1. And then we have density, which is kilograms, and then meters, -3, and it does not involve time. So now we have our dimensional matrix. We want to find the rank of this matrix, and we can do that using Python. And once we find the rank, we can figure out how many dimensionless numbers we're going to need through this equation I is equal, and I is the number of dimensionless, I is the amount of dimensionless numbers we're going to need. So I is equal to n, which is just the number of variables we have, minus r, which is the rank of our dimensional matrix. Using Python, the rank of this matrix is equal to 3. And we know we have 6 variables. This is the variables I listed out. So using this, we can determine that we need 3 dimensionless numbers to describe this situation. And what the rank also tells us is how many variables we need as a part of our core group. So since the rank is 3, we need 3 variables in our core group. So what the core group is a group of variables out of the 6 we have listed, or however many you have listed, that are a part of all of the dimensionless numbers. So in this case, like I said, we'll have 3 variables in our core group. In this core group, these variables will be in each of the dimensionless numbers. So for our core group, you have to have the 3 variables. They have to have all of the base units in them, and this will help. This is mandatory, so you can actually make the unit a dimensionless unit. So what I'm going to do is I don't want to have the mass transfer coefficient in because we want to isolate that, because it may we may want to see how that how this changes in accordance with this problem. So we're going to have that by itself. And then the other 2 that we are going to isolate are just kind of, you can pick and choose. But for ease, we're going to do the velocity, because it's the same base units as the mass transfer coefficient. And then we're just going to do viscosity. So that means, and our dimensionless numbers, I'm going to call pi1, pi2, and pi3. So I'll write this down here. And like I said, the 3 variables I decided to isolate were the mass transfer coefficient, the velocity, and the viscosity. So that means the 3 variables that are part of our core group is the pipe diameter, the mass diffusivity, and the density. So that means that those variables are going to be in all 3 dimensionless numbers. And these 3 core variables, to make sure that these numbers are actually dimensionless, they will be raised to a power. And we do not know what that power is yet, so we'll call it A, B, and C for this equation. We'll call it D, E, and F for this one. And then G, H, and I for the final one. Alright, so now we want to figure out what these exponents are, and we can do this since we know that these numbers are dimensionless. We know that there can be no units on this left side, and if there's no units on the left side, we know that all the units on the right side have to cancel. So we can make a system of equations and then solve for A, B, and C, or D, E, and F, and so on. So I'll start with pi 1. So we know the units of Kc is meters per second, so we know we're going to have at least 1 meter in 1 second, or 1 meter in the numerator, 1 second in the denominator. And we're going to start with making a system of equations for all of the base units. So this is pi 1, kilograms, meters, seconds. Like I said, we know that we have a meter in the numerator, so that would be a positive 1. Or the left side is going to be 0, but we know we have a meter, so we know we're going to have 1 there. We know we have a second in the denominator, so we can start our equation with the negative 1 here. And now we just go through and look at each variable and determine what base units it has and how it will affect our dimensionless number. So the pipe diameter is just meters. So since that is A, we can say meters is plus A. And then for the next thing, the mass diffusivity, it's meters squared per second. So we know that that has 2 meters in the numerator, so we can say plus 2b in the meters equation. And then C for the density has meters cubed in the denominator, so we can say minus 3c. And then that equation is done. So now we can do the kilogram equation. So the mass transfer coefficient does not involve kilograms, so there's nothing that is, there's no constant in that equation. And then the pipe diameter only involves meters, so there's also no kilograms there. The mass diffusivity also does not involve kilograms, so there's nothing there. And then finally we have the density, which does involve kilograms. It's plus 1 in the numerator, so we know C is just equal to 0. And now we still have our seconds equation. So for the seconds equation, we just do the same thing. We already have that, we have negative 1 from the mass transfer coefficient. Then we move on to the pipe diameter, which is 0. And then the mass diffusivity, which is negative 1. So minus 1b. Then we have the density, which does not involve seconds, so 0. And now we just solve our system of equations. So we know from this equation that C is obviously equal to 0. And from this one, we can figure out just minus b. Yeah, from this one we can solve for b. So if we just add b to the left side, we know b is equal to negative 1. Now we have C, we have B, and if we plug these into this middle equation, we can get A. So if you take a look at this, I have negative 1 for B, 0 for C, so we have 0 is equal to 1 plus A minus 2. So now if we solve for A, we're going to get A is equal to 1. And now we have our exponents for pi 1. So if I put the exponents into the equation we made for pi 1, I can come over here and say that pi 1 is equal to the mass transfer coefficient, since A is 1, times the pipe diameter, and B is negative 1, so divided by the mass diffusivity, and then C is 0, so density to the 0th power will always be 1, so it's not in this equation. And then we can take a look at pi 2. And since we have our core groups all to an exponent, in pi 1 it's A, B, and C, pi 2 it's d, e, and f. However, with pi 2 we know that the velocity has the same base units as the mass transfer coefficient. So it's actually going to be all the same exponents. So a is going to be equal to d, b is going to be equal to e, and c is going to be equal to f. So I can write out pi 2 right away. Pi 2 is equal to the velocity multiplied by, let's see, a is equal to d, so multiplied by the diameter over the mass diffusivity. And now all that we have left is to do the same system of equations for pi 3. And I'm running out of room over here, so I think I'm going to get rid of our system of equations that we did for pi 1. And we're going to do the same thing for pi 3. Use kilograms, meters, and seconds. Except this time we know our isolated variable is viscosity. So for viscosity we have a kilogram to the first power and then a meter in second to the negative first power. So that means each equation has a constant in it. So a kilogram is to the first power, so we got 1, and both of the other ones are to the negative first power. And now we're going to look at the exponents. So again, pipe diameter is just meters, so we have plus g. Mass diffusivity is meters squared per second, so we have minus h in our seconds equation and plus 2h in our meters equation. And then we have density, which is kilograms per cubic meter. So we have minus 3i in our meters, and we have plus I in our kilograms. And now we again solve for all the variables. So in doing this, we can see I equal to -1 right away, and we can see right away that h is also equal to -1. Now we can solve the meters equation by just plugging in. So if we plug in -1 for h, -1 for I, we end up getting 0 is equal to -1 plus g minus 2 plus 3. So now, if we solve for g, we end up getting g is equal to 0. Because if we add 2, add 1. Yeah, so g is equal to 0. And now we can write out our third dimensionless number, pi 3. Pi 3 is equal to viscosity over g is 0, so pipe diameter is not involved in this equation. Mass diffusivity, h is -1, so we have less mass diffusivity on the bottom. And then density, since I is also -1, density is on the bottom. So now we have our three dimensionless numbers that help describe this situation. And we can see that one of them is, since they're all dimensionless, you can do math with the dimensionless numbers just to get a new relationship. And what we want to do is we want to verify that we have the Reynolds, Schmidt, and Sherwood number here. So if we look at pi 2 and pi 3, they together contain everything that is involved in the Reynolds number. And we just need to combine them. So if we do pi 2 and divide it by pi 3, we end up getting, let's see, so pi 2 velocity times pipe diameter over mass diffusivity. divided by pi 3, or we can just multiply by the reciprocal. So we'll multiply by the reciprocal, which allows us to cancel the mass diffusivity. So that cancels. And then we're left with pi 2 over pi 3 equal to velocity times pipe diameter times density over viscosity. And we can see that that is just the Reynolds number. And now we have verified that we have all three dimensionless numbers: the Reynolds number, the Schmidt number, and the Sherwood number. And we'll use a relationship between these three dimensionless numbers in the next part when we are coding in Python and looking at experimental data.